In the last section, we looked at dot products. So now we're going to generalize dot products to inner product spaces. So in Rn, if I take the dot product of u dot v, yeah, we call that the dot product. But what if we extend this to other vector spaces? The general term is what we call an inner product. So that is also known, that dot product is also known as the Euclidean inner product. And it follows those rules that if I want u dot v, I would take u1 v1 plus u2 v2 until I get to u sub n v sub n. So that is an inner product. Specifically, it's the Euclidean inner product. Well, the general form of an inner product for some vector space is written like this, uv, right, with those little brackets around it. We define that as the general inner product. And an inner product can look very different even though they follow the same set of rules. So an inner product follows these four rules. Okay? The first one is that it doesn't matter which way I perform that inner product operation, I should get the same thing. So an inner product like this is the same thing as putting the v first and the u second. So it doesn't matter the order that I do the inner product, I should get the same thing. The second one, and you're going to recognize this from one of those dot product properties, is that if I take the inner product of u and the sum of v plus w, right, u is a vector, v is a vector, w is a vector, that's the same thing as taking the inner product of u and v and adding it to the inner product of u and w. And sometimes these inner products are defined exactly as Euclidean inner products, in which case it is a Euclidean inner product. But you can have inner products that are defined in other ways too, and we'll see a couple of examples of those as we go through. Suppose I take some scalar times an inner product. I'm going to separate those into two pieces, and here I'll attach the scalar only to the first piece. The second piece will stay as it is, and then I perform whatever operation I'm supposed to be doing. All right, the fourth rule is if I take the inner product of a vector and itself, whatever the inner product rule happens to be, it has to be greater than or equal to 0, and if it happens that that inner product is equal to 0, then that must mean that the vector itself is the 0 vector. So if you do the inner product of a vector in itself and you get 0, then you're talking about the 0 vector. Now, if you've got a vector space with an inner product, then we call that an inner product space. So a vector space with an inner product is what we call an inner product space. And that means that it has to follow those four rules. By the way, you can have what they call weighted inner products. Think of this as trying to find, let's say, a test average or an average for a class where the tests are weighted differently than the homework, which is weighted differently than discussion boards or something like that. So if you have something like this, where the inner product of two vectors u and v equals c1 u1 v1 plus c2 u2 v2. So these are now the components of that vector until I get to cn un vn. Those c sub i's are called weights. Okay, so you might weight the test average a certain amount or the homework a certain amount, and then those things would be called weights. So let's give an example here to determine whether something is an inner product. Okay, so let's look at the inner product of u and v defined this way. 3 u1 v1 plus 2 u2 v2. My question is it an inner product? Does it follow those two rules? Well, first of all, if I reverse it, if I take the inner product of v and u instead of u and v, then I get 3v1u1 plus 2v2u2. Is that the same? Yes. Okay, so that's okay. The inner product of u and v is the same as the inner product of v and u. All right, the second thing I need to test is I need to look at what the inner product of u and v plus w is. Okay, so let's see what that gives me. I'm going to replace all of my v's with v plus w. So up in the original function up here, I have a v here and a v here. I'm going to replace those with v plus w's, and then I got to carry through the operation. So I'll end up with 3u1 v1 plus w1 plus 2u2, and then I replace that v2 with the v2 plus w2. All right, let's distribute. So that'll give me 3u1 v1 plus 3u1 w1 plus 2 u2 v2 plus 2 u2 w2. All right, let's take certain pieces and combine them. Let's take this one and that one because they both deal with u's, and then I'll alternately take this one and that one. So that'll give me 3 u1 v1 plus 2 u2 v2, and then the second part will be this part and that part. So it'll be 3 u1 w1 plus 2 u2 w2. Now, go back to the original definition of my inner product. This first piece here, 3u1 v1 plus 2u2 v2, that's just the original vector space, right? That's the inner product of u and v as it was already originally written. What is this green guy over here? This is u1 w1, u2 w2. Isn't that u1 w1, u2 w2? That's just the inner product of u and w. Well, I was trying to show that the inner product of u and v plus w is equal to the inner product of u and v plus the inner product of u and w. Done. Works for that second one also. All right, the third thing I'm trying to show is how a scalar interacts with this Euclidean space, or with this vector space. So does some scalar times the vector uv equal a scalar times the first and the second? So I'm going to end up with a scalar times 3 u1 v1 plus 2 u2 v2. What do I get? I get 3 times the scalar times u1 v1 plus 2 times the scalar times u2 v2. Well, isn't that the same thing as multiplying the scalar times u and combining that with v? So here I'm basically treating that as one term and that as one term. And so I get c times the u vector, right? And then the second is the v. So yes, I've shown that. Basically, I've taken the constant and the scalar and brought them together. And then the fourth thing I have to show is that this vector and the vector gives me something that's greater than 0. So what happens if I take the inner product of the vector and the vector? Well, I end up with 3 v1 v1 plus 2 v2 v2. Well, that gives me 3 v1 squared plus 2 v2 squared. This has to be greater than 0. And so, yes, it works. unless the vector is equal to 0, right? It's possible that I'm dealing with two 0 vectors, and then I end up with, just 0, but other than that, it's going to be greater than 0. So yes, it fits the definition of an inner product. All four of those rules hold, even though this is not a Euclidean inner product, right? A Euclidean inner product would not have those 3's and 2's before it. It would just be u1 v1 plus u2 v2. All right, what if I had this inner product? Okay, so I'm going to define this inner product as the inner product of u and v equals u1 v1 minus 3 u2 v2. Well, I chose a vector kind of carefully. Suppose I try this vector as 2, 5. I could run through all the properties, but I think maybe the easiest one is to see if I can take the inner product of the vector in itself and get something that's greater than 0. So if I try the inner product of the vector with itself, right, that'll give me 2 times 2, right, first component times first component, minus 3 times second component times second component. Well, this gives me 4 minus 75, negative 71. No, the inner product of the vector in itself is not greater than 0, which means that it's not an inner product space. All right, let's take a look at functions. Can functions be inner product spaces? Sure, why not? So let's look at two functions. I'm going to use the vector notation for f to represent f of x and g to represent g of x, and I'm going to say those are two continuous functions on the interval from a to b. So let's define my vector space like this. So let's define the vector space f and g as the integral from a to b of the product f of x times g of x dx. And I want to know, is this an inner product? Well, first of all, I've got to be able to flip them around and get the same thing. So the inner product of g and f is going to be the integral from a to b of g of x times f of x dx. Well, yes, it doesn't matter which order I do that integral in. I'm going to get the same thing, so I'm okay. The second thing is, let's try taking the inner product of f and g plus some other function. I don't know, I'll call it h. All right, so I'll also introduce my h vector as h of x. Well, what does this give me? This gives me the integral from a to b of f of x times g of x plus h of x. Well, what is that? That is the integral of f of x times g of x plus the integral of f of x times h of x. This first guy here is the inner product of f and g. This guy here is the inner product of f and h. So does the inner product of f and g plus h equal the inner product of f and g plus the inner product of f and h? Yes, it does. Right, the third question deals with what happens when I throw a scalar in there. So if I throw in a scalar to this operation, what does that mean? That means it's a scalar times the integral from a to b of f of x times g of x dx. Well, isn't that the same thing as saying the integral from a to b and move the scalar to the inside of the integral, right? C times f of x times g of x. So basically this becomes the first term of my inner product. So that is equal to the scalar times the first vector operated with the second vector. So sure. The fourth thing is I need to know that the inner product is greater than 0. So the inner product of the vector and the vector is greater than 0. See if that works. So the integral from a to b of f of x times f of x is the integral from a to b of f of x squared. So yes, this has to be greater than or equal to 0. So it meets all four criteria, right? If you're squaring something, then it's at or above the x-axis. What's the area between that and the function? It has to be greater than 0 unless you're at the point where it's just a horizontal line, y equals 0, and then it's equal to 0. But either way, it's not negative. Right, one thing that comes out of these inner products is that there's a length of the vector formula that's sometimes a little bit easier to use and applies more generally to these inner products than the Pythagorean theorem one does. So if you know that you've got a vector, let's say that vector is 8, 15, and you want to find the length of that vector, then sure, you could say the magnitude of u is the square root of 8 squared plus 15 squared. If you remember your Pythagorean triples and right triangles, the answer is 17. Right? 8 squared is 64. That's 225. Add them together, you get the square root of 289, which is 17. 8, 15, 17 forms a right triangle. What if I did this? What if I took the magnitude of the vector by taking the inner product of the vector and itself and then taking the square root? So using the Euclidean inner product formula, this is what? This is 8 times 8 plus 15 times 15. Sure, I get the same thing. So why is this useful? Why do it this way and not just by the Pythagorean theorem every time? Well, what if you have an inner product that's not weighted, or that is weighted? That's the whole point of this. Then you're going to need to use that definition that I just gave you. Let's start with the standard ordered basis vectors in R2. So suppose my unit vector u is 1, 0, and my vector v is 0, 1, and I'm operating in R2. And I define this certain inner product to be what we had before. So the inner product of u and v is 3 u1 v1 plus 2 u2 v2. What's the magnitude of vector u? Well, you can't just say, well, I'm going 1 over and 1 up, so 1, 1, third side's the square root of 2, because your inner product is not defined that way. Your inner product is defined the way it was given in the problem. So you need to determine the magnitude of the vector by saying I want the square root of the vector and the vector. So the magnitude of vector u is going to have to follow that pattern that we gave up there. So it's going to be 3 u1 u1 plus 2 u2 u2. That's how I do the vector on itself. So what is my u1? Here's my u1. Here's my u2. So I end up with the square root of 3 times 1 plus 2 times 0 using the given definition of the inner product. The magnitude of vector u is just square root of 3. Now, what if I want the distance between u and v operating with that vector space definition on the top? So what if I want the distance between vector u and vector v? Well, the distance between vector u and vector v is the magnitude of u minus v. So the first thing I need to do is I need to find what that vector looks like. I need to find the vector that represents u minus v. Well, u is 1, 0. V is 0, 1. So I'll end up with 1, negative 1. This thing here is vector u minus vector v. Now I need to find the magnitude. Using, again, this definition that's up there. So what's the magnitude using that definition? It's the square root of 3 u1 u1 minus 2 u2 u2. Okay, so here's u1, here's u2. All right, so what does that give me? That gives me the square root of 3 minus -1 times -1 is 1, times 2 is 2. Oh, this thing should be a plus. Sorry about that. I didn't carry it down right. Then 3 plus 2 is 5. The magnitude of u minus v is the square root of 5, and that's also the distance between the two vectors. So sometimes it's important to know those other formulas, because when you get a situation like this where you're not in a regular Euclidean inner product space, then you are going to need those other definitions. All right, let's try one more, and then I'll do projection of the vectors as a separate video. Suppose I've got an inner product space that's defined in terms of integrals. And we did one like this before. The inner product space of f and g is defined as the integral from a to b as of f of x times g of x dx. But this time I'm going to say for f of x equals x squared, find the magnitude of f on the continuous function interval from 0 to 1. Now, what is the norm of f? The norm of f, or the magnitude of f, is going to be defined as the square root of the inner product of function f and function f on that inner product. So that gives me the integral from 0 to 1 of f of x times f of x. So f of x times f of x. And so this becomes the integral from 0 to 1 of x to the 4th dx. Ooh, remember integral rules. Antiderivative, so take x to the 5th, divide it by 5. And so that integral gives me 1/5. But we're not quite done yet, because I've left that radical out. So really what I want, that inner product is 1/5. I want to take the square root of 1/5. So I can write it as 1 over the square root of 5. If that makes you uncomfortable, you could write it as the square root of 5 over 5. Either way, that's the magnitude of f as defined in that inner product up there. All right, we'll do the second part in a minute.